We're going to do a couple of things that are not going to make a whole lot of sense as we do them because you're not going to really understand why you're doing them. You're going to use the skills we're building here in section 5.2 particularly. So this example asks us to write cosine of x in terms of the tangent of x. So what that means is at the end, I want to have cosine by itself on one side, and the right side have no other trig functions other than tangent in it. Okay? So you first have to choose a place to start. You have a couple of options. We could start with the reciprocal identities, but that would only take me from tangent to cotangent or from cosine to cosecant. We could use the quotient identities. Those are kind of iffy in this case because in the end I would have 3 trig functions instead of just 2. So I usually try to do those as a last resort. So that brings me to the Pythagorean. So if I look at the Pythagorean identities that have either tangent or cosine in them. So those are the kind of like where I'm going to start. I could start here. And the good news is I have cosine. And so I could get cosine by itself, but it wouldn't have tangents in it. What would it have in it if I solved this one for cosine? It would just have sines in it. And I don't want sines, and there's not an easy relationship between sine and tangent. So let's look at the other one that has tangent. This one has tangent in it. Well, the good thing about secant squared is that it equals what? 1 over secant is 1 over cosine. And so if I used that, I would have tangents and cosines, and I could go from there. So we're going to start with this identity, and we're going to try to play around with it until we can make some substitutions, and we can isolate cosine and have tangent on the other side. So let's start there. Let's start with 1 plus tangent squared equals secant squared. And I'm going to put the secant squared by itself right here. Now immediately, I like the tangents, but I want to get rid of the secants. Well, the quickest way to get rid of secant is to replace it with 1 over cosine, and then I'll have cosine. So that's what I'm going to do next. I'm going to replace this with 1 over cosine squared of theta. And that's the neat thing about the reciprocal identities is they will carry your exponents with them. So like if that had been a secant cubed, I could replace it with 1 over cosine cubed. That doesn't work for all of them. It doesn't work for the Pythagorean. You have to keep, Pythagorean theorem says you have to keep squares in your exponents. But any of the other identities, you can carry squares and cubes with you, which is kind of nice.
So all the 1 overs?
All the 1 overs, yeah. If you have an extra exponent, you just stick it on the new one as well. Okay, so that carries with us, and now we have this, 1 plus tangent squared. Okay? I want to get cosine by itself. So I'm going to put this here, and I'm going to cross multiply. And I'm going to have cosine squared times 1 plus tangent squared equals 1. And guys, we're just playing with algebra right now for the sheer sake of because the book said to. So do not think this is supposed to make a whole lot of sense to you yet. But I am trying to get cosine by itself. So if I divide both sides by 1 plus tangent squared, I have cosine squared is equal to 1 over 1 plus tangent squared. And bring your angle down each time. How do I get rid of a square? Square root both sides. So we square root both sides, and we are up to cosine of an angle is equal to plus or minus, and then you always split up that square root. You do square root at the top, which is just 1, and square root at the bottom, which is 1 plus tangent squared. Okay? And then avoid this. The square root of 1 plus tangent squared is not 1 plus tangent. You can't take the square root across addition and subtraction. You have to leave that square root there. So technically, I'm finished. It's what it said to do. It said get cosine by itself and in terms of. So it said equal to. That's what it means. Cosine equal to. Cosine in terms of means equal to. So equal to a bunch of tangents. So you're allowed to have numbers and you're allowed to have tangents. So that's what we have here. However, you're not allowed to leave square roots on the bottom. So we do have to rationalize that, and that will bring us up to cosine of theta is plus or minus, multiply top and bottom by the square root of 1 plus tangent squared. And what will it make happen on the bottom? When you rationalize, the square root simply disappears. So you have 1 plus tangent squared. That is what your book was asking you to do. I have no idea why they wanted you to do it, but that is what they asked you to do. They asked you to play around with your identities, start with something, isolate cosine, and on the other side have only tangents, and that is exactly what we did. So I'm going to pause here, let you mull it over. For our next problem, we want to write 1 plus cotangent squared of theta divided by 1 minus cosecant squared of theta in terms of sines and cosines. And then we want to simplify that problem and clean it up so that there are no quotients. First, before we do that, we need to make sure we understand what no quotients means. That means no denominators. So it's a multi-step thing here. So the first thing it wants you to do is change it all to sines and cosines. Then it wants you to perform some algebra and simplify it. And then it wants you to clean it up so that there are no quotients. So that's a lot of things it wants us to do. So we're going to start with the problem 1 plus cotangent squared of theta over 1 minus cosecant squared of theta. The first thing we're going to do is we're going to change all of our trig functions to sines and cosines. That's what it told me to do. It said put it in terms of sines and cosines. So we're going to start with 1 plus cotangent squared. Cotangent can be changed to sines and cosines by replacing it with the reciprocal, the quotient identity. Cotangent equals what? Cosine divided by sine. And you just carry the squares with it. So you replace cotangent with cosine over sine. And you carry the squares with it. You can carry squares through to any of your identities that are reciprocals or quotients, but you cannot carry them through to Pythagoreans, so be careful. All right, now it says 1 minus cosecant squared. Well, cosecant can be turned into 1 over sine. So that would be 1 over sine squared. So now it looks even worse. Now we have complex fraction inside of a fraction. And for those of you who have forgotten from college algebra, you are about to learn how to fix that. And the way you fix a fraction inside of a fraction is you multiply the top and the bottom by the common denominator of all of the little terms. So the common denominator of the top is, what's the common denominator on top? Sine squared. So you multiply top and bottom by sine squared. And that happens to also be the common denominator of the bottom. Guys, look, there are 4 terms. This one, this one, this one, and this one. And all 4 of them have a denominator of either 1 or sine squared. And the common denominator is sine squared. So you multiply top and bottom by sine squared of theta. And then you are going to distribute that into that fraction to every term on top and bottom. This times this times this. Well, that becomes sine squared plus, guys, when I multiply cosine squared over sine squared by sine squared, what happens to the sine squareds? They cancel, and I'm just left with sine squared plus cosine squared. Well, that's very convenient. Yeah. And on bottom, we distribute, and we have 1 times sine squared is sine squared. And if I distribute this, if I have negative 1 over sine squared times sine squared, that gives me just plain negative 1. Okay, so it brings us to here. We have accomplished the first step so far, okay? We've looked at it, we changed it all to sines and cosines, we got rid of the complex fractions, we cleaned it up a little bit. Can it simplify further? Yes. And the answer is yes, because sine squared plus cosine squared is an identity, and that equals 1. So now we're down to 1 over sine squared theta minus 1. The question is, how do I get rid of that denominator? You have to recognize, and this is something very difficult for students to recognize, that anytime you have a sine squared, it deals with this identity. sine squared plus cosine squared always equals 1. But that's only one of 3 ways you could write that. If I wanted to, I could subtract what from both sides? Okay. What if I wanted to move the 1 over here? And what if I wanted to switch places with these two? How could I do that? Subtract, yeah. So I could subtract the 1, and I would have sine squared theta minus 1 equals negative cosine squared of theta. Ran out of room there. So if you have a Pythagorean identity, you can rearrange it into multiple forms by adding and subtracting things to opposite sides. Now look at what I have. Sine squared of theta minus 1 equals what?
Negative cosine squared.
And we can make a substitution there, so that now we will have 1 over negative cosine squared. So going back to our problem over here, we'll bring this up here, and we will make this substitution. Just kind of box it off. We have 1 over negative cosine squared of theta. Well, what is 1 over cosine? Secant. So that's really negative secant squared of theta. That is what your book was asking you to do here. One more time from the top. They said, take this problem, change it to all sines and cosines using your identities. We did that. Then we got rid of the complex fraction to start simplifying. We multiplied top and bottom by the common denominator, distributed it in, we got this. We applied the identity, sine squared plus cosine squared, and we got 1. The denominator looked like a variation of that Pythagorean identity, so we went off to the side. We rearranged it so that we had sine squared minus 1 on one side, and we figured out that that was equal to negative cosine squared. So we made that substitution. Then we said, okay, we're not allowed to have any denominators, but I can always change a trig function from a fraction by using its reciprocal. So we said 1 over cosine was secant, so therefore 1 over cosine squared was secant squared. We just were left with negative secant squared.
So is that the answer?
So that is what they were asking you to do. You will get bogged down sometimes, but later on in section 5.2, you will have a better idea of where you're going. So, we have one more problem, you guys.
You can't.
Where is this right?
Okay, so guys, I picked this problem out of your book. It's not one you have to do for homework, but it's similar to some you have to do for homework. And these problems have the same directions as the example we did just before. They say, write in terms of sine and cosine, simplify and clean it up so that there are no denominators, no quotients. And I just want you to see a couple. We'll do this one and maybe one more before we just call the section over. Okay, so we are starting with 1 plus cotangent all over cotangent. How many people want to just cancel out the cotangents? That's so common. But you can't do that because the cotangent there, if you look at that, it's a piece of a binomial. So you cannot cancel unless you can cancel from both pieces on top. Okay, so that's not an option. But it doesn't matter because they asked us to follow a specific set of rules. They said change it all to sines and cosines. So we're going to do that first. So I'm going to take the 1 plus cotangent and replace it with 1 plus cosine over sine. And then I'm going to take the cotangent on bottom and replace it with cosine over sine. Now we have fractions inside of fractions. And the easiest way, regardless of what you've been taught previously, once you get to this point in math, the easiest way to get rid of what we call a complex fraction is multiply top and bottom by the common denominator of every term. Well, we have 3 terms. We have 1, we have cosine over sine, and we have cosine over sine. The common denominator is sine. So go and multiply top and bottom by sine. Distribute it into the top. And when you distribute to the top, you will get sine plus what?
1.
Sine plus cosine, right? The sines cancel here. Okay. Sine plus cosine over, and the good thing on bottom, if I multiply sine by cosine over sine, the sines cancel and I'm just left with cosine. That brings us to here. People really want to cancel out those cosines. They want to say, oh, that's just sine theta plus 1. That is not what that equals, okay? So at this point, you're kind of stuck. Do y'all understand that? You're like, I have no idea what to do. I have to get rid of that cosine, but it's stuck underneath those 2 other things. But have y'all ever seen a fraction taken apart? Like, if this was 1/5 plus 3/5, I could put that together and make 4/5, right? People never think about it, but you can take a fraction back apart. You can take the first term over the bottom
And second.
and the second term over the bottom. And once you do that, you're allowed to cancel those cosines out once you split it into a single term over a single term.
And then sine.
And sine over cosine equals
Tangent.
tangent.
Another one equals 1/2.
Alright, now that's not a tangent squared, so be careful, that doesn't equal secant. It only equals secant if it's 1 plus tangent squared. The Pythagoreans have to have their exponents to stay that way. Alright, one more time, look at this. We started with 1 plus cotangent over cotangent. And we just proved that it must be equal to tangent of theta plus 1. Turns out there are lots of things in trig that are equal that you would never think are equal. And we're going to spend a lot of time playing with that in section 5.2. Do you guys need to ask a question about this one?
Okay, instead of doing all that work, can we just put 1 over cotangent plus cotangent over cotangent, the same answer?
Yes, I was actually going to talk to you about that. The only reason I didn't was because your book told you to change it all to sines and cosines. Does that make sense? Okay, so they want you to walk through it, but that's a really good point. If they hadn't said, like, you know, sometimes they're just giving you weird directions. Do this first, then do this. If they hadn't said that, we could have started this problem by splitting the fraction. 1 over cotangent plus cotangent over cotangent, and then the cotangents cancel immediately, you know? And so we have, and that becomes tangent. The problem with that is it happened to go straight to the exact same answer that we got over here, but sometimes it doesn't. And so if your book is specific, then do it a specific way because they're trying to lead you to a certain answer, or through a specific skill set that will help you in the next section. But yeah, they're always, if you got stuck on a test and didn't know what to do, I would definitely try to do that.
Would you have homework instead of doing the whole process? Is that-
For now, I would like you to do the whole process, okay? I really would because it's gonna help, they're trying to help you work with fractions. And that's what really bogs people down in the second. But if you do get stuck, certainly try to do it an easier way.